Welcome back, class. Today we are going to wrap up our discussion of Chapter 6, talking about diffusion and effusion, and also we'll talk a little bit about when gases become non-ideal. So, what are these diffusion and effusion concepts that are introduced? Well, if we remember back to kinetic molecular theory, one of the sort of overarching ideas is that a gas molecule or atom, gas particle, will move around and in a straight line until it hits either the Waals or another molecule and then move off in another direction, right? Have these elastic collisions and move. And so we can sort of envision the movement of a typical gas molecule looking something like this, where it's kind of haphazard. It goes from one place to another, but definitely not, if we're, say, starting down here at this corner, right, it is not going to make its way up to this corner in a straight line, right? It's going to have to take this very sort of non-straight path, right? It's because it's going to hit things, encounter things, and move, and eventually it will make its way over there. It'll make its way throughout the container, but it has these very short paths that it moves and then changes direction, etc. Now, the average distance between collisions, right, is called the mean free path. And of course, this is going to be dependent on how many particles there are, the density of those particles, right? It's how often it hits something. Now, the two concepts, the two processes that we're going to talk about, diffusion and effusion, sort of are connected to this idea of the gas molecules moving around, right? This mean free path idea. So the first one, diffusion, is something that I think you're probably familiar with. And this is the idea that a collection of molecules spreading out from an area of high concentration to low concentration. So, let's imagine that we introduce some gas into a room. Say it's, a fragrant gas. And we introduce it down in this corner here. Now, if you're located near that corner, you're going to smell that gas fairly rapidly. But if you're located over here, right, it's going to take some time for a molecule to make its way, here, because it's going to take this sort of zigzag path maybe and eventually get there, right? As it hits other molecules, bounces off, etc. So when we have, say, odors, molecules that are, odorous in a room, such as, somebody sprays perfume or some other type of odor, right? People farther away will take longer to smell it because it takes a while for those gas particles to make their way through the room. Because remember, while we can't see it, they're constantly encountering other air particles, right? Whether they be nitrogen or oxygen or carbon dioxide or water vapor, right? This sort of sea of gas that we're surrounded in, this atmosphere. And so that's the idea of diffusion, is that it will eventually spread out, but it takes a little time. It's not a straight line from point A to point B. Now, the second process, which we'll spend a little more time on because we have a calculation or equation we can work with, is called effusion. And this is one that probably not so familiar with and is a little more what we might call esoteric, right? It's not something that we encounter very often. And this is called effusion. And this is the process by which a collection of molecules escapes through a small hole into a vacuum. So if we imagine that we have a sample of gas, but on this wall there is a hole. The key is, and over here on this side is where, we imagine our vacuum to be. So we have this area of low pressure, we have this area of higher pressure, right? So how rapidly will these molecules make their way through this hole to get to the other side? Now, of course, we know that if there was a large opening here, the molecules would rapidly flow, right? Because they're going to move from the area of higher pressure to lower pressure, right? They're going to move to try to equalize the pressures, right? That's the idea. And so, but if we only have a tiny hole for them to escape, how fast will they make it through? And that's this idea of this rate of effusion that we refer to. Now, where might one see this? Well, we could imagine, say, we're on a spaceship and we get a tiny hole in the hull, right? And the idea is, if the inside of that spaceship is under sort of a normal pressure, like an airplane, right? I mean, we could think about it as an airplane as well. You know, we have lower pressure outside the airplane, or if you're going to go to the extreme, the spaceship, where you have maybe a true vacuum, right? If we get a hole in the side, how rapidly will the atmosphere inside escape outside, right? That would be an effusion idea, right? Now, a similar concept can be sort of applied to the idea of, say, a balloon. If you fill a balloon with helium, right, a latex balloon or a rubber balloon, right, as you blow it up, you get tiny holes that form, tiny gaps between, the rubber, right, which, aren't enough for the balloon to instantly inflate, but the gas inside there will eventually make its way out, right? So a helium balloon, right, eventually deflates, right? Even a balloon filled with air eventually deflates, right? Not because you pop it, but because the gas escapes through tiny holes. And this is that same idea, right? Where there's, higher pressure on the inside of the balloon, lower pressure outside, you get these particles moving through these tiny holes through this process that we can think about as effusion. So what can what we've learned sort of tell us about effusion? Well, one thing that we've learned, right, is that the velocity, or how fast molecules are moving, is related to their mass, right? So heavier molecules will have a slower velocity. Well, if we think about heavier molecules moving slower, right, slower moving molecules are going to have less collisions, right? It's going to take them longer to have the same number of collisions. And so they are going to encounter this hole less often, right, if you have less collisions. So we might presume then heavier molecules are going to have a harder time effusing through that hole, and therefore they're going to effuse more slowly. And that's exactly, what happens, right? If we look at the equation, we see that the rate is inversely related, right, to the mass. Right? There's an inverse relationship. And so, larger mass equals slower effusion. Now, this equation, so-called Graham's Law of Effusion, is set up so that we're comparing the rates of two gases, right? So we're always going to be looking at the relative rates of one gas to another, and it's related to the ratio of their molar masses, right? Okay, so let's put this into action. Let's use our Graham's Law equation here. So let's say we have a sample of N2 gas that effuses from a container in 42 seconds. How long will it take the same amount of I2 gas to effuse under the same conditions? Now, this problem's a little tricky, right? So what do we put in for our rates, right? We don't actually have a rate here. We have a time, right? Now remember, a rate is typically an inverse of time, right? It's some amount per time, right? So you might say that, 1 mole per 100 seconds or per hour or whatever, it's a rate. So the rate is actually, you might argue, if we're comparing the same amount, is actually equal to 1 over the time of effusion. Okay. So we'll come back to that in a second, right? And that'll be important when we go to set up our calculation. So now let's look at our equation. So let's just set it up, and it really doesn't matter, but I'm just going to set it up with the N2O as gas A. So we're going to have the rate of effusion of N2O over the rate of I2, and that's going to equal, that's going to equal the square root of the mass of I2 over the mass of N2O. Now, coming back to our idea here, right? So if the rate is actually equal to 1 over the time, then what I can write here is 1 over, 1 over the effusion time of N2O divided by 1 over the effusion time of I2 equals our ratio of masses. Now, you can also write this, right? So we could do this, right? And we could leave it this way, but if we have the ratio of inverses here, this is the same thing as writing the time for I2 divided by the time of N2O equals, that's of I2, the mass of N2O. Right? So this idea of, how is the actual effusion time different than the effusion rate is going to play a role here. So now that we have a form of the equation that we can utilize with time, now we can start to solve our equation. Now, before we get too far, we do need the masses, right? So the mass of N2O, right, equals 2 nitrogens, 1 oxygen. So that equals 44.02 grams per mole. The mass of I2 equals 2 iodines. So that's 2 times 126.9 grams. So that's going to be 253.8 grams per mole. So I'm going to come over here, and so my time iodine is what I'm trying to find. So my time of I2 over 42 seconds equals square root of the mass of I2, 253.8 grams per mole, over 44.02 grams per mole. So if we go through and do here a little math, we get 2.4012, and I'm keeping some, a few extra significant figures. What's the time of I2 over 42 seconds? So if I solve for the time I2, it's going to equal 2.4012 times 42 seconds. Now, notice this is no units because they cancel out. So if I do that, I get the time that would take I2 to effuse would be 100.85 seconds. Now, significant figures, right? Notice this time is only given to 2 significant figures here. So we're going to have to round this to 2 significant figures. It's a little tricky here. That would be 100, right? It's hard to do that with 100, so we really need to put this in scientific notation. So it's going to be close as we can get. It's about 100 seconds. And to 2 significant figures, we would write it like that. Yeah. So it takes about 100 seconds for I2 to effuse under the same conditions, which makes sense, right? It's longer, as you would expect, with the mass, being obviously heavier, right? So, Graham's Law of Effusion. We can start to see, and really we can see, it's not so much the time it takes, but it's this idea of the connection between the mass and how this rate of effusion, and that connects back to the relationship between mass and velocity that we've looked at before. All right, so that's effusion and diffusion. Now, the last topic I want to talk about here is we've been working under the ideal gas law. Well, gases are not always ideal, right? When we start to deviate too much from sort of normal, quote, conditions, we start to see deviations from the ideal gas law. Now, when do those deviations occur? Well, typically, those deviations occur when we get to high pressures and or low temperatures. Now, why is this? Well, if we remember under the kinetic molecular theory, it states that there are no attractions between the gas molecules. So they hit, they just move away, right? They don't stick, right? Well, as we start to move, especially if we think about lower temperatures, right? The gases are moving slower, so they spend more time interacting with each other, right? So maybe the interactions really are there, right? As we get at higher pressures, right, we start putting the gas molecules closer and closer together, right? Maybe they start to have actual interactions, right? As we get... So we start to lose some of these assumptions of the kinetic molecular theory, which assume these, quote, ideal conditions. And we also make the assumption under that theory that the gas molecules don't take up any space, right? That we can sort of ignore the volume of the gas molecules themselves, right? And essentially say that, we have this amount of empty space. But again, as we get to high pressures, they start to occupy an actual significant proportion of the volume of our sample as we start to put these things under higher and higher pressure, And so we start to deviate again. So again, at this point, I'm not asking you to do a lot of this, but we just want to maybe understand that as we get to higher pressures and or lower temperatures, we start to deviate from, quote, ideal behavior. Now, what does that mean? Well, in theory, it means that the answers that we would calculate for, say, pressure and volume, for example, are going to deviate from what we would get from the ideal gas law. So let's look at a sample problem. So let's say we want to calculate the pressure exerted by 1 mole of chlorine gas with a volume of 5 liters at 0 degrees Celsius or 273 Kelvin. So it's a pretty easy calculation, right? We know that pressure equals nRT over V. And so we have P equals 1.00 mole times 0.08206 liter atmospheres mole Kelvin, 273 Kelvin. Now, under these conditions, right, Kelvins cancel, moles cancel. Divided by, divided by our volume, which is 5 liters. Of course, then our liters cancel. And we end up with if we sub the top, 22.4024 liter atmospheres divided by 5 liters. Liters cancel. We end up at 4.48 on top of each other equals 4.480 ATM. Okay, so that would be what we'd calculate assuming ideal conditions. Now, there is another equation, right? It's called the van der Waals equation, and it applies these correction factors, right? So we first of all make a correction for the fact that gas molecules can actually occupy a volume, right? So we make this correction, which is the number of moles of gas times this value B, which we have a table over here of this B and A, right? And these, as you can see, depend on the gas. And we can make a correction to the pressure that corrects for the presence of actual interactions between the molecules. And this is, again, this A factor times the moles over the volume squared. So it's essentially, right, if we think about how it differs from the ideal gas law, right, PV equals nRT, right, we can see we've made a correction to the P value, we've made a correction to the V value, and the nRT part is the same. Okay, so let's then see if we can calculate the pressure using the van der Waals equations. Now, I'm probably not going to ask you to do this too much, but just so we can illustrate the point here. So we're trying to solve the pressure, so I'm just going to write P plus. So if we look at the table for chlorine, right, this is what we're interested in. Our A factor is 6.49, and notice the units are going to be strange for these, liters squared, atmosphere over mole squared, times moles over volume, right? We had 1.0 moles, 5 liters squared. So we have that term, and this is times our volume, right? 5 liters minus our 1 mole times the B factor here, which is 0.0562 liters per mole. And this equals nRT. Now, I'm not going to write all that out. Right? I'm going to point you to the fact that what we did up here, this nRT term here, right, is going to be the same nRT term. So I'm just going to write this as what we got here, and that was 22.4024 for these conditions. And the units there would be liters times atmospheres. Okay, so now we can start to work the math, right? So if we do this part, we can get P plus, if we start to do our math, right? Notice, look at the units. If I square these, I'm going to end up with mole squared over liters squared. And so eventually my liters squared would cancel. My mole squared would cancel. And so if we do the math, 1 over 5, or 0.2 squared, times 6.49. So 1 divided by 5, it's 0.2 squared, it's 0.04, times 6.49. We get 0.2596. Oops. And what are the units going to be? ATM, right? Which makes sense because we're going to be adding pressures. We got times. So we got 5 minus 1 times 0.0562, or essentially 5 minus 0.0562, which equals 4.9438. And the units here, right? Moles cancel here and here. So we have liters minus liters, so of course our units are going to be liters, as you would expect. Equals 22.4024 liter atmospheres. So let's divide by the V here. So we're going to get pressure plus 0.2596 ATM equals, we're going to take the 22.402 liter atmospheres divided by the 4.9438 liters. Okay, 22.4024 divided by 4.9438, and we get 4.5314, let's say. And of course when I do my division, my liters will cancel, and this will be ATM. And so now to get my pressure term, it's just pressure equals, I'm going to subtract this from both sides, so 4.5314 ATM minus 0.2596 ATM. And so the ultimate pressure equals 4.272, right? So we're going to do this to 4 significant figures based on, our temperature is the lowest number of significant figures, right, at 4. So 4. ATM equals the pressure. So if we compare the pressure we calculated by the ideal gas law and the pressure calculated by the van der Waals equation, we could say there's not a huge amount of difference here, but we're not at, huge conditions, right? The biggest influence here is where it's slightly lowered temperature. We're not at extremely high pressures by any means, and so you wouldn't expect a huge amount of deviation here. But we can see how we're going to get a slightly different answer here using the van der Waals equation. And the van der Waals equation is a better equation, right? It is more accurate, right? It builds in these correction factors, right? And that is the type of equation that somebody that wants a higher level of accuracy, wants a better calculations, they'll use the van der Waals equations in even more advanced equations to calculate pressures and so forth when building, say, like plants and chemical plants and these kind of things, where you're not going to rely on a simple ideal gas law equation to do your calculations, right? It is a approximation, right? You're assuming these things that we've talked about in the kinetic molecular theory are true. And they are pretty true under sort of normal conditions, but they're better calculations. We just don't really need to use anything more sophisticated for the types of problems that we're doing, right? The answers are going to be reasonably close enough for our purposes using the ideal gas law. So, behavior of, quote, real gases as opposed to ideal gases. Okay, well, that wraps up Chapter 6. Make sure that, again, you're following along, that you're doing the homework, that you're watching these videos along with other videos that I put up there to, build on these concepts, give you different perspectives, etc. If you follow the outline on Talon, you can, not make sure you're not missing anything, as we're only in class, a limited amount of time. All right, next time I talk to you, we'll be discussing Chapter 7.